Okay, so a new lecture. So good afternoon, everybody. So let's start. So last time I told you what you are gonna see in this course. Okay, so what I told you guys last time is because this course is about digital systems, and digital system means ones and zeros, nothing else. That's why in this course, all the time you are going to see ones and zeros. And this is a reality for any digital system. We only use ones and zeros. This is number one. Number two, you're going to see hardware, because this course is mainly about hardware. How can we do some operation by the hardware? And this is actually processors, or that's how computer works. So if you write your program in Java, in C, or whatever, your program has to be executed by the hardware. Addition, subtraction, and other operations should be done by the hardware. Is that okay? However, you are not gonna, hardware actually means transistors. This is how all the digital system, or even all the electronic devices we have are made of transistors. Okay, you are not going to see transistor in this course, because as I told you last time, we are going to mainly use logic gates. We're going to use logic gates. Okay, something like this. This is a gate. I'm going to tell you how it works. In lab number one, you are gonna use this gate. This gate is inverter. Sometimes we call it a NOT gate. So, but I want you to understand, behind this gate there is electronics. Okay, it's outside the scope because our focus here is only on one and zeros. Okay, but you should understand, for every gate we have here, there is an electronic circuit that can do the operation we're doing here in logic, in ones and zeros. There is some electronic circuits that can do it. For example, multiplexer. Okay, I'm not explaining what is multiplexer now. I'm going to explain it later, but you should understand it should have a circuit, or so everything I'm going to teach, like multiplier, adder, or whatever, should have some electronic circuit this way. But this is out for scope of this course. We only are going to focus on the logic part. Okay. The other thing I explained last time, and that's also what you need in the coming lab, is if I have an inverter this way, so this is a gate. This gate should work this way. If the input is zero, logic zero, you should get one inverter. So if it is one, you get zero. Is that okay? So this logic, this gate has only one input. Okay, this input can be 0 or 1. If the input is 0, you get 1. If you put 1, you get 0. Is that okay? So this in logic, I'm gonna say 0 and 1, and I'm gonna say gate. But in electronics, what 0 means, what 1 means. Okay, so actually what happens, we take two voltages, because we have two cases here, 0 or 1. So actually we take two voltages, and we take, for just an example, we take 0 volt and 5 volt, just an example. Okay, and then I can or the electronics can decide 0 volt means logic 0, 5 volt means logic 1. Is that okay? That means if I put here, based on what I explained here, if I put here 0 volt, I'm gonna get 5 volt. If I put here 5 volt, I'm gonna get here 0 volt. Is that okay? So, by the way, and someone last time asked me this question, by the way, I can make it the opposite. I can make, it doesn't matter. Okay, what I mean here, I can make 5 volt means logic 0, and 0 volt means logic 1. It doesn't matter, because anyway you have two voltages. I can use one for logic 0 and you can use 1 for logic 1. Is that okay? So what's important is the logic operation has to be done. If I have AND, so regardless what voltages you are using, it has to do the operation of AND, okay? As I'm going to explain later. But I think most of the chips are using 0 volt and 5 volt. 0 volt for logic 0, 5 volt for logic 1. And now, to be more accurate, actually, logic 0 is not only 0 volt. To be more accurate, you get what I'm saying? It's a range of voltages. For example, I just show an example here. Any volt from 0 until 0.3 volt, anything in this range will means logic 0. Is that okay? Same thing for logic 1. It's not only one value, it is a range. So anything starting from 4.3 until 5 volt, anything here, any voltage here means logic 1. Any questions? Good. So yeah, that's what I'm saying. In this course, I want to design a logic circuit. This logic circuit, for example, just an example, when I give here 2 inputs, A and B, this logic circuit should decide which one is bigger. Okay, that's why I call it a comparator. So in this course, we will learn how can you design this circuit. You are going to implement these circuits in labs. Okay. Same thing here. How can you design using logic gates? Okay, that's what you are going to learn here in this course. For now, I'm gonna for sure today. I'm gonna give you more. These are the main, the basic or the main gates. The first gate is not. We have another one. We call it OR gate and AND gate. So these are the basic ones. Using these gates, we can do everything, as you will see in this course. Okay. So I think in today's lab, you are gonna use this inverter. The way this inverter works is here. The way this inverter should work, as I told you, here we make a table like this one. This is the input X, and this is the output X prime. Okay, so this is the input, and this is the output is here. And then I say the input here is only 1 bit. So it has only 2 cases, either 0 or 1. It cannot be, it's just 1 bit. So it can be 0 or 1. This is all the cases we have for input, okay? So if the input is 0, the output should be 1. If the input is 1, the output should be 0. Is that okay? By the way, this is a very important thing. We're going to use it all the time. And this is what we call a truth table. Truth table. So what is truth table? Very simple. Truth table, it has the input. This is the input, okay? And also it has the output, the result. But it should have all possible cases for the input. Here, because we have only 1 input, I have only 2 cases. In other, if you look at this here, for example, if I have a circuit like this one, okay? I have a circuit like this one here. This circuit has 3 inputs and it has 1 output, okay? So these are the 3 inputs I have, A, S, P, as you see here. So these are the 3 inputs we have, and this is the output we have. So this is a truth table. We're going to use truth table all the time in this course, because truth table actually is telling you how this circuit is working. For each possible input, tell you what is the output. Okay, so here we need all possible inputs here, and based on what I told before, if you have 3 inputs, how many possible outputs you can have out of the 3 inputs? 2 to the power of 3, as I said before. So 2 to the power of 3. So that means I should have 8 cases. These are all the possible cases here. This 8, all possible cases for the input. Okay. So again, this is the input is here. Okay, so again, because I have 3 inputs, we should have 8 cases, and these are all the cases we have. Okay, and even last time I told you how can you generate them. Look at the pattern. You remember 0 1 0 1 0 1, 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, 4 ones. Okay, so this is what we call this all possible input. And for every input, here you can know the output, or you can calculate the output, whatever. This is what we call a truth table. Okay, for every logic circuit, or for every gate, in order to describe how this circuit works, in order to understand how it works, we are going to use what we call truth table. Another thing also very important we are using, we call it, in addition to that's what we are going to use all the time in logic, in digital system, truth tables. Truth table, and this truth, as I told you, this truth table has all possible cases. I put all the possible cases. Okay. Also, we are using what we call timing diagrams. Also, this is, we do it also all the time in digital system. Timing diagram. So what do you mean by timing diagram? Something like that you can see, and that's what I think that's what we are going to do in the coming lab. So in timing diagram, for example, if I have an inverter here this way, okay, so this is the input. The input can here. This is the input. I'm gonna apply this signal to the input. This signal is a binary signal, 1 and 0. Okay, that's what we're gonna do all the time here in this course, as I told you. So like 0 1 0 1 0. So this is, I'm gonna apply this input to this is signal to the input, and then what should be the output? If you apply this one, what should be the output? And that's what we are going to do in the coming lab. The output has to be something like that, inverted. Okay, so if it is 0, so here for this signal, guys, this is the time. X-axis here is the time. Y-axis is the voltage. So during this time, the voltage is 0. Here the voltage is 5, 0, 5, 0, 5, and so on. Okay. In other words, during this time here, this is logic 0, logic 1, logic 0, logic 1, and so on. Okay. So if this is the input, I have to see output this way. Okay, because it's inverter, has to invert the input. Is that okay? Okay. Now you should, and that's what you are gonna do in all labs, including this week labs. Okay, lab. So how can I generate this signal? I need to generate this signal to input it to the circuit I have to test the circuit, something like that. How can we generate it? To generate it, there is something called function generator. Okay, so function generator can be it's a device. In your case, you can use an external device for function generator. So what is function generator? Function generator is actually a device. This device generates signals. These signals can be analog signals, something like that, or it can be digital signals. Digital, it has to be this way. Okay. For sure, as I told you in this course, all the time we're gonna use digital signals. So there is a device. This device is called function generator. This function generator is already in your lab. The lab has already external device for function generator, but I think you can use the discovery tool. So the discovery kit has a function generator. Okay. So now I want to see, because maybe some of you don't have this basic knowledge. Okay. So if you have here, if you have a signal like this one, okay. So from here to here, you know, this is a cycle. This cycle is repeated, as you know. So from here to here, this is the period. The time is t, and the frequency is actually 1/t. Frequency is 1/t. Is that okay? And this is t. There is another term. We are getting. So here, so this is like voltage 1, and this is voltage 2. What? Okay. And there is another term I want to explain here. It's called a duty cycle. Duty cycle. The duty cycle actually is T on divided by the total T. This is the T on. How big is this time over all time? Okay. We can make it, you can multiply by 100 to make it a percentage. So that means if the duty cycle is 50%, what it means? It means the time of the on is half. Okay, half. So that means on and off are equal. This time is equal this time. If it is something like 90%, you should see signal something like that. 90%. The on is very, very long. If it is just 10%, you should see something like that. The on is very short. Again, I think most of the time we are here in logic circuits, we are gonna go with 50%. Okay. Also, any questions? Yeah, sure.
So if the ones and the zeros have to be alternating, but what if you have two ones in a row? Is there a way to dictate that in your digital signal?
No, function generator does not make that.
So there's no two ones in a row, right?
No, function generator don't do that. You get what I'm saying? Function generator is gonna do, function generator means it's gonna generate a periodic signal. So it has to be this way. Okay. But that doesn't mean it doesn't mean you cannot generate, or the output of your circuit cannot be 1 and 1. For sure it can happen. That's a different story. But here I'm talking about function generator. Function generator, okay, generates periodic signals. You got to see all the time this way. This is a function generator. Okay, there is another thing you should see in the lab. There is something we call it offset. So what offset means, okay? So quickly, offset means so for example, if the signal is this way, okay? So here you can move the signal up and down, you shift. That's what we call offset, okay? So if by changing the offset, this signal can come here, you can shift it up or down, okay? Up or down, but when you change the offset. So the offset is like a DC voltage you add to your signal. So you can shift the signal up or down, okay? This is what it's already, there is a button, you can find button in the function generator for the offset, okay? So you can bring, it depends for sure, again, here in digital system, we try to keep V1 the same voltage as logic 0, and V2 the same voltage for logic 1. Okay. One of the things also you should see in the coming lab is, and I think I explained it last time, when I tell you we have a signal like this one, for sure this is not very accurate. That is for sure, because nothing can change from 0 volt to 5 volt in 0 second. Okay, nothing in the world can change this way. Speed cannot change this way. Temperature, nothing can change from a certain value to other value in 0 seconds. So in reality, and I think that's what you see in the coming lab, in reality, it should be something like that. Yeah, this is actually what you should see. Yeah, this time may be a very small time, but there should be a time. And this time we call it rising time. And the time here to fall is called falling time. And this is something you need to measure, I think, in the first lab. I told you last time, it's here between 10% to 90%. So how much time it needs to for the signal to increase from 10% to 10 to 90%. This is a rising time. Falling time is actually from 90 to 10%. Okay. Any questions? One more thing here is about propagation delay, because that's what you are going to see. Here, I told you if I input this way, the output has to be this way. For sure, it can't be this way, because that means it takes 0 seconds. The transistor or the circuit is going to take 0 seconds to, it's going to react. Once it is 5, it's going to react just in 0 seconds to 0. This is not the reality. The reality is there is a delay. So in reality, what you have to see is, and that's what you have to see in the coming lab, for sure there is some increase here, decrease here, okay? And then once this one is not going to respond right away, okay? So it's going to take some time, and then this one is going to go low after some time, and then also it's going to slow a little bit here, okay? So the propagation time, and that's here we measure it from 50% here until 50% here, okay? So this is, for example, this is the input of the inverter, and this is the output of the inverter. So there is a delay. The the time between here to here, that this time is called TP propagation delay. But when the signal moves from high to low, when it moves from high to low, there is another one here. We call it propagation delay. When the output it changes from low to high. Is that okay? And I think there is a question in lab one. I'm asking you, what are the factors that can impact this delay? One of the factors that can impact this delay, in addition to the circuit itself, and there are some circuits are faster than others, so it means on the circuit itself. There is another important factor is the stray capacitance. Stray capacitance. What happens is that if I have a gate like this one, and then I connect a wire, this at the input. This wire itself, it has a capacitance. This capacitance, we call it a stray capacitance. So it's like you have a capacitance here. And you know, if you have a capacitor, it's gonna take some time to charge this capacitor and discharge. Okay, so this is also one of the things that can impact this delay. Okay. Any questions? For every chip you have, okay, make me wanna go see. Yeah, I'm explaining it here in chapter 2. Okay, swap here. Okay, so here this is for every chip you have. You are gonna use chips like this one. Logic chips, something like this one here. For every chip, there is what we call a data sheet. Okay, I have posted on iLearn the data sheet for all the chips you have. Very important to read the data sheet. The data sheet is going to give you every information you need about the chip. Okay, so for every chip, for example, this is an inverter. So for example, in this chip, as you see here, this chip has how many inverters? 1, 2, 3, 4, 5, 6. You might not need to use all of them. Okay, you can use only 1, 2, 3, whatever you want to use. Okay, so if I want to use this chip, for example, look how can use it. Number one, if you want to use any chip, for example, if you want to use this inverter, so this is pin number 13 is the input. Pin number 12 is the output of this inverter, okay? But for any IC or for any integrated circuit, you have to connect power here. Otherwise, it's not gonna work. So here you have to connect VCC. I think it's 5 volt. You have to connect ground here. So in order to be able to use these logic circuits, you have to make sure you connect power for C and ground. Okay, the data sheet is going to tell you how much voltage exactly, but I think it's 0, 0, and 5. Is that okay? Once you connect 5 volt and 0 volt here, you can just use it. So just put here 0 volt and measure this one. You find this one 5 volt. If you put here 5 volt, you are going to get here 0 volt because this is an inverter. Is that okay? So now the question is that how I can know. So here this is pin number 1, pin number 2, pin number 3, pin number 4. So how I can know the pins? How I can locate the pins? Very simple. Sometimes you can see something here. You can see something like a din here or something like that. Sometimes for the chip, sometimes they put a dot this way. Sometimes they make something like that here. So this should tell you have to count this way. I think I told you this last time. So 1, 2, count one. For example, if this is 5, so this one should be 6. Okay, you have to count this way. Okay. Very important. You know how you have to know how to count. Otherwise, you may damage it. If you connect it in a wrong way, you may damage it. So you have to be careful. Okay, or it does, at least it doesn't work with you. Okay. I told you function generator is a device used to generate signal, periodic signals. Function generator. There's another device you need to use, because I think in the coming lab you need 2 things. You need to generate signal and also you need to see the output. So if this is here, yeah. So here you can generate this signal using function generator. In order to see this one, in order to see the signal, So here you need to connect this one to the function generator. The output here has to connect to a device, we call it oscilloscope. Oscilloscope. Have you ever used oscilloscope before? You know what is this? Since it's not everybody. So anyway, so oscilloscope is a device that's used to display signal. So if you want to display the signal so that visually I can see it, you can use the oscilloscope. Discovery Kit should provide function generator and oscilloscope for you as well. Okay? The other thing here that may be related to lab 2, I want to also explain here is okay. So something. So for example, if you have here inverter here, and I have another inverter here, is that okay? What's important in this case, the volt, if the first one, if the output of this first one is logic 0, the second one has to interpret it as logic 0 as well. Okay? How I can make sure of that? I have to make sure the voltage resulted from the first one compatible with the second one, right? Otherwise, if the first one generates 0, the other one may not take it as a 0. It's not going to work, right? So how it works this way, I'm going to tell you how. So for the output here, it is actually something like that. Look here. So this is the ground, 0 volt, and this is VCC, which is actually 5 volt. Okay. So we have here V output low maximum, and we have here V output high minimum. So there is something we call V output low maximum, V output high minimum. Okay, you can find this number in the data sheet. So the data sheet is gonna tell you the maximum output. If the output here is logic 0, low, this is the maximum voltage, and if the output here, okay, is high, is 1, so this is the minimum voltage. It can be, so it's actually from here, it's gonna be from here until 5. Okay, so this is for the input here. Okay, for the input here, what happens here is we have here 0 volt, we have here 5 volt. Okay, but what happens here also, we have something we call it V input low maximum. Okay, so anything here in this range is gonna be interpreted as 0, logic 0 at the input. You got what I'm saying? So if you want to input here logic 0, you have to make sure the voltage, the input voltage here in this range. Okay? So you can see the output low maximum is already in this range. So it should be okay. It should work. It's compatible. When this one in the first one, when the first one outputs 0, the second one will take it as 0. Okay, because it is in this range. Same thing here. Same thing here. We have also a range here. This one is called V input high minimum. So this is a minimum voltage that can be interpreted as input. Is that okay? Any question? Yes.
So what happens if it's in between?
That's a very good question. So because we are talking about transistors, we are talking about the transistor is used like a switch, either open or close, okay, in order to do logic. So the correct thing is the voltage has to be either in this range or this range, because we have either 0 or 1, right? It shouldn't be here. So the voltage shouldn't be here. But regarding question, this is, we call it interdeterminant region. So this region, we call it interdeterminant region, okay, or undecided region, or it shouldn't be here anyway. Okay, you can. I want you to, this is the purpose of the lab. So in the lab, try to change the input and see what's going to happen when it comes to this region. What's going to happen? Okay. So again, if you want to use it like a logic circuit, it should not be here because it can make errors. It's not going to work as a logic circuit. You get what I'm saying? So the transistor is not going to be totally open or totally closed. Okay. So anyway, so it has to be either here or here. Any questions? You understand the idea? They have to be compatible. That means the output low maximum here has to be in this range, and also have to make sure the output high minimum here, the minimum has to be in this range. Okay, so that when one gate outputs 0, the other one is going to take it 0. Okay, if outputs 1, the other one takes it 1. So there is something, I think this is in lab number 2, you need to measure, we call it noise margin. Noise margin. Noise margin actually here, this part here, from here to here, we call it, this part here, we call it noise margin in case of low, in case of 0. And here, okay, so this is this part from here to here, that's what we call noise margin in case of high. What this means, make it easy. I'm gonna make it easy. I'm gonna tell you the idea. The idea is that the output is here, right? Because of the noise, the output can move to here. Still, it's okay. It's still logic 0. It's gonna work, no problem. So move to here, no problem. Move to here, no problem. Move to here, that's a problem. You get what I'm saying? So in other words, we can. This is how much noise we can tolerate. Okay. So if this is the output, if we have noise in this range, your circuit is going to work correctly. More than that, no, it's not going to work. You understand what I'm saying? So the bigger the noise margin, for sure the better. It's a better. Okay. Any questions? You understand what I'm saying? Same thing here. This is the voltage is here because of the noise. The noise can push this voltage down. So the maximum it can push up to here. To take it still it is 1. Once you enter this area, I don't guarantee it's gonna work. Any questions? This is what we call noise. Yeah, sure.
What causes noise most of the time?
Oh, many things. There are many factors. Like for example, the light, especially if you have some coil, it's gonna make electrohysteria. Many things including, for example, magnetic field. There are some magnetic field around us everywhere. So if you have a wire, this wire can capture some electromagnetic, can generate some voltage. You get what I'm saying? And other reasons, but this is one of the reasons. So noise is something normal around us everywhere. You should understand better in electronics. You get what I'm saying? For me as a digital guy, I don't care. As long as it is in the range of 0, I don't care. As long as you are in this range, I don't care. As long as in this range, I don't care. As long as it's still 0, I'm okay. Okay. I think one of the questions in chapter 2 is about why we need to know the propagation delay. For sure, the propagation delay is going to tell you how fast you are going to get the output. For example, if you have a delay here 1 nanosecond, so if I apply input here, how much time is gonna take until I get the output here? There is a delay here and there is another delay here. So if the delay here, for example, 1 nanosecond and another 1 nanosecond here, so in total it's going to be 2 nanoseconds. Okay. I think there is another question, and maybe I quickly I want you to think about. It's telling you about in logic circuit we have what we call maximum operating frequency. There is a maximum frequency you can use. You get what I'm saying? So this maximum frequency you can use. It's related to TB high low and TB low high. I'm going to tell you quickly why or what I mean exactly. I told you here for this output to change, if I have input this way, okay, if I have an input this way, it's going to take some time until the output here is going to respond. So there is some delay here, as I told you. Okay. This delay, the bigger or the longer the delay here, the shorter the input frequency I can use. What is the relation? By just common sense, what is the relation? Very simple. The relation, I can't make the input very quickly, very quick, okay? Shorter than this time. It can't because it didn't finish it, the first one yet. So because it takes some time to flip the first one. Before you flip the first one, I give you the second one. You got what I'm saying? By common sense. So this delay put a restriction on the maximum frequency. At least I have to make sure, because before I give you the second pulse, you already finished the first one. Very simple, okay? So anyway, I want also to do some search about these basic things, about what is the relation between the delay, propagation delay, and frequency. Do some search about it. The other thing also we are going to do in the coming lab, there is a simulator. A simulator you already downloaded. It's called digital. This is very interesting simulator. You can draw any logic circuit. You can put the input. You can get the output. You can analyze the circuit. Simulator, very useful for you. Okay. So in lab number 2, I ask you to simulate a circuit, and I give you a tutorial about it just to make sure you are using it. Okay. Any questions? Good. So I think that's more than enough here. Again, I'm gonna say it one more time. There are two important things we are gonna use it all the time. Truth table. We're gonna use it all the time. Truth table. The second thing we're gonna use it all the time. Timing diagram, something like that. Timing diagram. So these two things can tell you how the logic circuit, or can describe how the logic circuit works, right? How it reacts to the all possible inputs. Okay. The other thing here I want to teach in this chapter before I move to the next chapter, I just want to make a definition. This definition is about a binary code. So what binary code means, okay? So let me see here how I explain it, and then I give you some examples about binary code. So let's start with the first one here. A binary code is a pattern of ones and zeros. Pattern 101001 pattern. It's a pattern of 1 and zeros that is used to represent an element of information that is distinct among a group of quantities. Is that okay? So I have a group of pattern. So it's more than one bit pattern. 0101 pattern. So okay. So every element has this pattern. So let me give you an example to understand what I mean exactly. For example, there is something we use all the time. It's called ASCII code. This is one of the codes. So what ASCII code means? I'm going to tell you what it means. Okay. Look here. Very simple. We agree. Any digital system can only use binary numbers. Okay. Hard disk, memory, everything is ones and zeros. Okay. So now we have a problem. For example, if I have a letter A, and this is the computer can only understand ones and zeros. Okay. So here, if I have a letter A, so how I can send this information, letter A, to the computer, okay, using the keyboard. Same thing. If the computer is gonna send letter B or letter C to the monitor or the screen, okay, how it can send it, and the computer can't work with A or B or C or these things. Only computers can work on binary numbers. We agree on that, okay? So what happened is very simple. We need to convert every character and every letter we are using in the keyboard. I need to convert it to a binary number. Is that okay? So that every time you press A, I'm gonna send the binary number to the computer. Okay. And this number we call it ASCII code. Okay. Same thing. If I want to display B on the monitor, I have to send the code one and zeros related to B. So that's why every character or every letter you have here in your keyboard, it has a code. We call it ASCII code. So ASCII code stands for American Standard Code for Information Interchange. So an institution here in the United States in the very early in the beginning of computers, they decided to make this table, and this table is standard. Everybody in the world is using it. That's why if you buy a keyboard from China, it's gonna work because it's using the same table. Buy it from anywhere in the world, if it's manufactured in the United States, all of them use the same table here. For example, I can show you here. For example, if you have here a letter A, so the code for letter A is 41 hexadecimal. Okay, the letter lowercase a is 61. You understand what I'm saying? So for sure, I'm writing here in hexadecimal because it's more convenient for us as a human to give it to you in hexadecimal. But in reality, when you send to the computer, you have to send it in binary. Okay, as I said before. So this is one of the codes we are using now. So every letter here has every letter or every character has a different code. Okay, so this is an example for code. I'm gonna also give you. There are many other codes. Okay, and in the future, when you take more classes, especially for example communication, other classes, we use also several codes. Here, as also an example for what I mean by code is, I'm gonna give you what we call a BCD or binary coded decimal code. Also, I'm gonna give you what we call here a gray code. Okay, let's start with the Greek code, for example. Okay, the Greek code is the idea of the Greek code is it's a very simple idea. So the idea is that every digit from 0 to 15. Okay, you remember this is hexadecimal. That's what we did in hexadecimal from 0 to 15. Okay, so there is a code corresponding to each one of them. So 0, this is the code for 0. This is the code for 1. This is the code for 2. This is the code for 3. This is the code for 12. This is the code for 15, and so on. So every digit has a code related to it. Okay. So, but wait a second. We did that in hexadecimal. Okay. So hexadecimal, it was the same thing. Every decimal here had a code. That's true. However, there is something in hexadecimal that is not acceptable in some applications. Okay. What is that? This code is designed. If you look at how we made this code, this code is designed in such a way that when you change, every time you move from one number to another, there is only one change in one bit. As you see here. So it's not the case in the hexadecimal. For example, as you can see here, when we moved from here to here, there is only one bit change. From here to here, only one bit change. So always, so this code is designed so that every time you move from one number to the next number, there is only one bit change. Okay. However, in hexadecimal, this is not the case. In hexadecimal, for example, if you have this is number 7 and this is number 8. Look how many changes. We have 4 changes here. 4 changes to move from 7 to 8 in hexadecimal. Okay. Why this is attractive in some application? I'm going to tell you why. But again, the main difference between representing these numbers in hexadecimal and or gray code, hexadecimal, when you move from one number to another, there may be more than one change in the bits. But here, I force it to be only one bit, one change, one bit in the change. Okay. So why this is in some application it's interesting. I'm going to tell you why. For example, if you have a hardware circuit, if you have switches that changes these bits. Okay. So what happens is that, for example, I want to move from 7 to 8. So this is 0, 1, 1, 1. And then I'm gonna move from this one. This is if I use hexadecimal. It's gonna become 1, 0, 0, 0. If I use hexadecimal, okay. What happens is that because this data coming from switches, it may happen that one switch can be faster than others. So when I move from here to here, okay, I'm gonna get some number here by accident in the middle before I move. For example, to move from here to here, the switches are gonna take, for example, 1 millisecond. For example. So from here to here, it may take 1 millisecond, for example. Okay. However, because maybe some switches are faster than others, for example, this one can change, but these ones are not didn't change yet. So here, before you move from here to here, I can get some numbers in the middle. This can make trouble in some application, and they decided, okay, I'm not saying all the time. I'm saying in some application, when you move from one number to another, I need only one bit change. Otherwise, if Otherwise, I can have some number, valid number here in the middle. Okay. This problem should not happen here because to move from here to here, only one switch, or only one bit is going to change. Okay, or on one switch. Okay. But if we have multiple switches, maybe one switch is going to be faster than others, and this can lead to when you move from here to here, you are going to have some number by accident in the middle. Anyway, is this not the focus? Anyway, the focus is I want to teach code. What I mean by code, okay? The last thing here I want to teach also, we call it BCD code. So I'm going to explain what I mean by BCD code, okay? It's somehow interesting idea, but try to focus with me, otherwise you are going to get confused. I'm going to tell you what is the main idea here. Okay, let's start with what we call binary addition. That's what I explained before, binary addition. For example, I want to add 75 plus 35, okay? What, for sure, human beings don't use binary number. So what I'm gonna get from the user, I'm gonna get number 7, and then I'm gonna get number 5. Is that okay? And then I have to convert. Humans, you are using decimal numbers, okay? So what's gonna happen, I'm gonna get number 7, and then I'm gonna get number 5 from the user. So once I get 7, 5, I have to do some operation in order to convert this number to a binary number like this one, okay? Same thing for 35. Human is not going to give me this number. We don't like binary numbers, so I'm not going to give you this number. I'm going to give you 3 and 5, and then you have to convert it to this number. Okay? After that, you need to do what we call a binary addition. So here 75, this number is 75. This in binary, this number is 35 in binary, okay? And then after that, I have a hardware circuit that can do binary addition. Okay, after I did the addition, I'm gonna get the number in binary. I'm not gonna give this one to human because we don't like binary. So I have to do the opposite now. I have to convert this number, okay, to decimal. So it has to be 110. I have to give you 110. Is that okay? So this is what we call binary addition. I'm gonna do this addition in a different way. Okay, that's what we call BCD addition. I started with this one. Just I want you to understand. This is, and actually this one is white most of the time, but I think you also need to learn the other one as well. But here, what we do here, we call it binary addition. Any number you give to me, we have to convert it to a binary number. So this is a binary number, 75 binary number, 35 binary number. And then I am going to add the two numbers bit by bit. Then the result, which is 110 in binary, I have to convert it to this so that human can understand it, okay? Now, what I'm gonna do, I'm gonna do something like, I'm gonna do this addition, but a little bit in a different way, okay? So what I'm gonna do is, I'm not gonna convert, I'm not gonna get 75 this way. I'm not gonna do this way, okay? What I'm gonna do is, I'm gonna keep this number in decimal, but I'm gonna represent it in binary. Wait a second, what do you mean? I'm gonna tell you what I mean, okay? So this is 75, this is 75 binary, okay? In BCD, okay, I'm gonna keep the format of the number in decimal, but I'm gonna represent it in binary. Okay, I'm gonna tell you what I mean. Look here, that's exactly what I'm gonna do. Look here. Here, this is a 5, this is 5 here. And this is 7, so this is 7 here, right? So I'm gonna keep it like binary, but I'm not gonna represent it in binary. So this is 7 and this is 5. For sure, this is completely different from 75 I had before. So 70. So here, it's two separate numbers here. So here, this one is 7. If you make conversion here, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. This is a binary number. You are gonna get 75. But what I'm gonna do, I'm gonna keep the addition. I'm gonna keep the addition in decimal, decimal. Okay. But I'm going to represent this number in every digit alone in binary. So what I did here, this is number 5, this is number 7, separate. This is number 5, this is number 3. So this is 5, 5, 3. So every digit, I'm going to represent every digit alone, not the whole number. Every digit. This is the main difference. Not 75. Every digit is going to be in binary. Okay. And then after that, what I'm gonna do is, I wanna do like decimal addition. That means, look here what I want to say. This is 75 and this is 35. Look here. Because this is a digit, this digit is decimal digit. Decimal digit, but it is represented in binary. Okay? So this digit, it has to be a number from 0 to 9. It can't be 10, right? Because this is a decimal number, but I represent it in binary. It's not a binary number. If it's a binary number, in the 4 bits, I can represent the numbers from 0 to 15. But now, because this is a decimal number, every digit has to be between 0 and 9. It cannot be 10. You understand what I'm saying? So anyway, so this is number 5 alone. This is number 7 by itself. This is number 3. And then this is number 5. Is that okay? And now I'm going to do binary addition, bit by bit, binary addition, normal binary addition, bit by bit. After you do that, look here, 1 plus 1 is 0, 0, 0, and we have 1. Okay, so 1, 0, 0 is 1, 1, 1, 0, and then we have 1 here. Okay, and then 1 plus 1 is 0, and then we have 1, 3 ones is 1, and then we have 1 here, 1 plus 1 is 0, and then we have here, I got this way. Okay. For sure, look at the trick here. Number 1, if these digits, if every digit here, if every digit less than or equal 9, I'm done. It's correct. Okay. Can you give me example? I will give you example. For example, I'm gonna do 12 plus 12. Look how this one is gonna work. Okay. So 2 is actually 0, 1, 0, 0. 1 is actually 1, 0, 0, 0. 1, 0, 0, 0. Is that okay? And then 0, 1, 0, 0. Do the addition, it becomes 0, 1, right? Sorry, 0, 0, 1, 0. This one becomes 0, 1, 0, 0. Okay? So because this digit less than 9, and it has to be less than 9 because this is actually decimal number, but I represent it in binary, so this one is okay. This one less than 9, it's okay. And now let's look at the result. This number is 4, and this number is 2, 24. Okay, so we don't have problem here. The problem can happen when, after you add these 2 numbers and the result more than 9. Okay, because you are doing here a binary addition. In these 4 bits, you can have 10, you can have 11, 12, 13, 14, 15, right? And this is not allowed in decimal numbers. Is that okay? What should I do if it is? So what happens in this case, I'm going to do one step adjustment. We call it adjustment. So once I do the adjustment, this adjustment is going to, because this is a decimal number. So after 10, I have to move 1, and there should be 0 here. Okay, so I'm going to do adjustment. In this adjustment, what you have to do is, as you see here, I'm going to add, because if this one, listen to me, if any digit greater than 9, so I'm going to add 6 to this number to make the adjustment. If the number less than less than 9, do nothing, just add to 0, just add zeros. Okay, but in this case, because this number is 10, right? And this number also is 10 and 10. Okay, because this number is greater than 9, I'm gonna add 6 to make adjustment. Here, this one I'm gonna add 6 to make adjustment. If this number less than 10, okay, I'm gonna put 0, 0, 0. So now, after you finish, you need to do adjustment, okay? Because you added binary just to keep this number here between 0 and 9. Okay, the adjustment you have to do, if the number here is greater than 9, you have to add 6 this way. If the number here less than 9, you just add zeros, put zeros. Okay, and then you do another binary addition here. 0 plus 0 is 0, 1 plus 1 is 0, and then we have 1 here. 1 plus 1 is 0, and then we have 1 here. 1 plus 1 is 0, and then we have 1 here. It's going to move from here to here. Okay, 1. 1 plus 0 is 1, and so on. If you do this way, you are going to get correct result, which is 100, 110. Again, you got what I'm saying? So again, I'm going to represent every digit in 4 bits, and then I have to force this number to be between 0 and 9 because it's a decimal number. If you do the addition and if you find the number is greater than 9, you have to do adjustment, okay, to correct it, okay, this way. But someone can ask me, why you add 6? Why it's not 7? I'm going to tell you about the trick. What is the trick? Look here, very easy. Because this is 4 bits. A carry is going to be generated here every 16. Every 16, a carry has to be generated, right? But in decimal numbers, you should have a carry this way every time it is greater than 9. Okay, so if this one is 10, if I get here 10, okay, so it has to be 0, and then there is 1. 1 has to go to the other one. Okay, so what happens here is that's why I need to add 6. I need to add 6 here so that I generate. If you get 10 and you add 6, it becomes 16. So 16 you get 0 and then you generate a carry. So again, the idea here is that in decimal, I'm gonna have a carry every time the number is greater than 10. But in here, the way I do it here, okay, you are gonna generate a carry every 16, right? So that means if this number is 11, so I have to add 6. Once you add 6, it becomes 17. Okay. Out of the 17, as I told you, every 16 is going to move as 1. So the result will become 1 here. Is that difficult? You understand what I'm saying? So anyway, let me tell you the conclusion. The conclusion here, this is not a binary number. Okay. This is digit. Here, the numbers are in decimal format, but I represent every digit in binary. Is that okay? And I do binary addition. Once you do the binary addition, now I have to make sure these numbers are not greater than 9. Okay? How can you make sure of that? Anyone that's greater than 9, I have to add 6. By adding 6, you are going to trigger a carry here. For example, if the result is 10, I'm going to hit 0 and there is a carry here, which with the same thing I have to do in this one. If the result here is 12, if it's 12, you add 6, okay? Every 16 is going to go here as well, okay? So I'm going to get 2 and then I'm going to get 1 here, okay? Anyway, so I need to do some adjustment, okay? So it's like, so this addition is similar. It's similar to you are doing a decimal addition, okay? Decimal addition. Anyway, that's enough. Any question? This is not the main purpose. The main purpose here is just to teach you what I mean by codes, okay? But still, you need to learn the difference. You should understand the difference between binary addition. I give you this example here. In binary addition, the number 75. Okay, this is 75. So the whole number is 75. I didn't convert the 7 alone, the 5 alone, and the 7 alone. I didn't do that. Okay, if you keep it this way, 7 and 5. So actually, this is a decimal format, but I represent it in binary because computer can only understand binary. Anyway, so these are 2 different approaches for addition, but I think most of the time we're going to use this one. But maybe in the future, we're going to have one lab or whatever about BCD numbers, something like that. So I want you also to understand it. Any questions? Yeah, sure.
If only one of the red ones right there is greater than 9, do we need to add 6 on both of them, or just the one that's greater than 9?
Only the digit that is greater than 1, you have to put 6. The other one, you put 0.
Okay, so
And then you have to put 0 and then add everything together. You know, once you put 6, that means you have to generate a carry here. Because this one is greater than 9. Because it's greater than 9, I have to send 1 here. You get what I'm saying? So the digit, if you have, for example, 5 digits here, okay? The digit that's greater than 9, you put 6 under it. The digit that's less than 9, you put 0. 4 zeros. And then you do binary addition. It will be good. I want you to, when you go home, just to play, try different. Yes, sure.
35 in binary on that last slide.
Yeah.
In the slide before. If you go to the slide before, 35 converted to binary is wrong. It's not the right binary.
Is it 35, right?
No, in the last slide.
Oh, last slide?
Yeah.
It's not 35? Okay, this is, anyway, I will check it. but I'm not sure why you are very confident this way. So this is 1, this is 2, 8, sorry, 4, 8, 16, 32. So 32 plus 3 is 35. Because this, okay, you maybe what's confusing you, I'm not converting 5 alone and 3 alone. It's just one number. That's why this is a binary number. The other one was not a binary number. It's a decimal number, but I represent it in binary format. Okay, so this is 1, 2, 4, 8, 16, 32. So 32 plus 1 plus 2, 35. And the other one, it's 4 and 4, but this is number and another number. Anyway, so it's good you asked this question because I'm quite sure you will be confused. What is the difference between what I did here and what I did the other one? Okay, this is a binary number. The other one is not a binary number. It's a decimal number. Any questions? Okay, so I think that's enough for chapter 1. I'm gonna start chapter 2. Okay, so here in chapter 2, okay, sorry. Okay, in the first part here of chapter 2, I'm gonna explain basic Boolean operations and Boolean functions, okay? Let's see, start with the first one here, okay? So let's start with the Boolean operation or gates, okay? The first operation here, we call it NOT operation, okay? Or inverter. So this is, okay, so let me, because in this part, I'm gonna teach what we call Boolean algebra. Boolean algebra. How this algebra is different from the algebra you have been using before is here, this algebra is applied for Boolean variables. And Boolean variable means ones or zeros. You got what I'm saying? So what I did before, you can add, you got addition, you can do the multiplication, you can do things like that in normal algebra. But this algebra is, I'm gonna do operations, okay, logic operation on Boolean variables. So here, every variable I have, whatever, if you want to call it, for example, variable X, this variable is binary variable or Boolean variable. So this variable can take one of two values, either 0 or 1. Is that okay? So again, this is Boolean algebra. In Boolean algebra, we have variables. These variables are binary variables. And then I'm going to teach what kind of operation I can do on binary variable. You will see some similarity with the normal algebra, like addition, subtraction. You will see some similarity. Also, you will see some differences. Okay, but you should understand what we're doing here. It's not. I'm sure you will be confused because you may apply. It's a normal algebra here. You'll find it makes mistakes. Here we are talking about algebra, but for binary, for Boolean variable, ones or zeros. Okay, and I'm not going to do addition. Instead of addition or multiplication, I will do other operation. The first operation I can do is called not operation. Okay, so the first operation I can do it on a variable. For example, if I have a variable called x. This is a Boolean variable. Again, as I told you, it can take value from 0 to 1. I can say, for example, z equal x prime. This is an operation. Or sometimes, by the way, we can put a bar this way. It's the same thing. So if you see a bar or c prime, it's the same thing. This is an operation. So what this means? It means the variable x, the variable z is equal to not or the inverted value of x. Okay, what this means, I'm going to tell you what it means. Look here. So z equal x prime. That means if x equal to 0, okay, so that means x prime should equal to 1 because this is not operation or inverter. Okay, x prime, that means z should equal to 1. If x equal to 1, x prime should equal to 0, and z should equal 0. Very simple, very easy. Okay. So this is how I can represent it in Boolean algebra. But using logic circuits, I'm going to use this logic gate. So to implement this operation, okay, we're going to use this logic gate, okay, which is called inverter. Any questions? And this is the truth table of this one. This is the truth table. The truth table should give you the input and the output. This is all the possible cases for the input. So here, because the input is only one variable, it can be 0 or 1. If the input is 0, output is 1. If the input is 1, output is 0. Any questions? Okay. Also, I told you there is what we call timing diagram. So if I input something like that to this gate, I should get something like that, as you see here. Okay. Again, remember, this is the time. This is the time. So during this time, it was logic 0. During this time, logic 1, logic 1, logic 0, logic 1, and so on. Okay. You can see here in this timing diagram or truth table. We are going to use them all the time to describe to you how the logic circuit or logic gate, how it works. Okay. So as you see here, when this one was 0, the output was 1. When it was 1, the output was 0. Flip, right? 1, 0, 0, 1, 0, 1. Is that okay? This is how this gate is. How this is a definition. This gate works this way. Okay. Any questions? Let's get one more gate, our next gate. So always this inverter has only one input. Always this one has only one input, and it has one output all the time. Okay. And this is how it works. You make a triangle this way, and then you put a bubble here. Okay. Okay. Now I'm gonna come to end, logic end. So there is this, as you see here. This is how, as a gate. This is how we draw it as a gate. Again, please try to understand what I'm saying. And can be a gate. And this is a gate. Okay? Or it can be an operation in Boolean algebra. Right? And this operation, if I want to implement it using hardware, I have to use this gate. Okay? So if this is an operation in Boolean algebra, what is the symbol you are using? So as you see here, guys, look at this one or this one. Sometimes as I say Z, variable Z equal XY. This is not X times Y. We don't have times here. This is not normal algebra. This is X and Y. This is not times. Okay. We don't have times. Okay. Or sometimes I make it this way: X and then you put a dot Y. So if I put either one of them should be, it means and. That means I have a variable X, a variable Y, and then I'm gonna do AND operation. The result is gonna go to Z. Is that okay? Okay. So how this one works, how this operation works, I'm gonna tell you how. This is the truth. Again, to understand how it works, we need to look at the truth table. Okay. So using gate, as you see here, we have X and Y. This is the input of the gate. The output of the gate is gonna be X and Y. It's not times. We don't have times. X and Y. Okay. So how it works? Very simple. And you can think about it in our normal life, in our daily life. When I tell you have to do this and this, is that different when I tell you have to do this one or this one? That's exactly what we're gonna do right now. So when I say this one and this one, you have to do both, right? But when you say or, means one of them should be enough. If you do both, okay, that's more than what I need. One of them should be enough. This is a logic. That's exactly what we're gonna do. So look how it works. So that means here, as you see here, this is a truth table. In order to get one, all of the input have to be 1. So in order to get one, okay. Otherwise, I'm gonna get 0. So if only one input, you can think 0 means you didn't do the condition. I asked you to do left 2 and left 3. You have to do both of them. If you do only one of them, so one of them is gonna become 0. Okay? So anyway, in order to satisfy the condition, you have to do both of them. So again, the way this logic works, very simple way. Look here, guys, very simple. The only way to get 1 here is by having 1 and 1. Anything else is 0, right? I'm gonna say it in a different way, and this can make the calculation easy if you understand it. Listen to me. I can put this way. If I have a gate and I know one input is 0, don't look at this not other one, it's a 0. Don't look at the other one. Once you find one input 0, don't think about it, it's 0. Don't look at the second one. I don't need the second one. You understand what I'm saying? So again, the only way to get one, both of them are 1. If one input, at least one input is 0, again, this is how AND works. I make here analogy for it. It's like you have two switches this way, two switches. In order to connect point 1 and 2, the two switches has to be connected. And connected here means 1. So it has to be 1, 1. If one of them connected, but the other one is not connected, so point A is not connected to point 2. It's just analogy to understand the logic here. Okay. Any questions? So if you do this operation again, guys, very simple. If I find one input 0, don't look at the other ones. Don't look at the other ones. It's a 0. That's it. Is that okay? Same thing. Yeah. So for example, I show here a timing diagram here. Look at the timing diagram. When it was here 0, 0, I got 0. When at the time when one was one of them, this one input was 1 and the other one is 0, I got 0. When the both inputs are 1 and 1, I got 1. 0 and 1 is 0. 0 and 0 is 0. Okay. Any questions? Or is different. When I tell you do this one or this one, so one of them should be enough. If you do this one, okay, you satisfied my condition. If you do this one, you satisfy me. If you do both, okay, it's still okay. So this is how OR works. This is the symbol we're using for OR. This is a symbol for the gate. But how using Boolean algebra? Here we do plus. But again, when I say Z equal X, I'm not saying plus because this is again. This is not normal algebra. We are not gonna do multiplication or addition. This operator here means OR. Okay, so here the operation I'm gonna do X or Y and store the result in Z, or Z equal X, Z equal X or Y. Okay, how it works, as I told you, very simple. Because it's OR, if one input is 1, I'm gonna get I'm sorry. Oops, I'm sorry. Here I put the truth table for AND. I'm sorry. I'm gonna correct. So this is the truth table for AND. If you look at the truth table of OR, I'm gonna correct it. For OR, here is actually, let's see. Okay, so here if one input is 1, so the result is 1. If one input is 1, it is 1. If both of them are 1, I'm gonna get also 1. The only way to get 0 when the two inputs are 0. Okay, I'm gonna correct this one. I just repeated the truth table for AND, not OR. So in case of OR, it is enough to have only one input is 1. Okay? To make the calculation easy for you, look how it works. If I want to do the, once I find one input is 1, I don't need to check the second one. Just the result is 1. You understand what I'm saying? So when you do the calculation, once you find this variable is 1, don't waste your time and look at the other one. 1 means the output is 1 right away. If it is 0, I'm going to check the second one, right? So again, very simple. In case of AND, if one input is 0, output is 0, right? Right away. The only way to get 1, both of them are 1s. Okay. For OR, if one input is 1, okay, the output is 1. At least one input. Okay. The only way to get a 0 here when the two inputs are 0s. If I want to make analogy, if I want to use this logic to make analogy, so it's going to be something like parallel switch this way. So to connect point A to 2, it's enough to have one switch closed. If two switches are closed, okay, that's more than what I need. At least one of them should be. And this is the timing diagram for OR. Look here, 0 or 0. This is the only condition I'm going to get 0. Here, once I have 1 here, I'm going to get 1 here. Okay. Once I have 1 here, 1 and 1, I get 1. Here, 1, I'm going to get 1. Okay. Any questions? So this is an operation like multiplication, division, as you did before. But here, this operation is a logic operation. Okay. So once you have a binary variable, Boolean variable, do the operation, you need to know how can you get the result. Okay. Last thing, nothing. Just in 1 second, I want to explain it. Also, always this and or always it has only one output. I told you in case of not. Always it has one output, it has one input all the time. But in case of and, okay, it always has one output, but it can have more than one input. Same thing for all. But if this is the case, how it works? It's the same logic I have just explained. So that's why I give you one example here. I know some of you are, so here guys, please listen to me. What I'm saying is that, okay, but I give you a truth table for 2 inputs. Now I'm giving you the truth table for 3 inputs. It can be 4, it can be 5, it can be 6, it can be 1 million if you can design it. It's okay. When I just give you example for 2 and 3, but it can be more if you want. Anyway, so how it works, because this is n, the same thing as I explained to you before. If one input is 0 from any, for example, if I want to calculate this one, guys, look here, and that's what we're gonna do it all the time. By the way, I'm trying to help you by a shortcut or an efficient way to do the calculation. Look how I'm gonna calculate. This input is zeros. I don't even need to think about the other inputs. Done. Once this input are zeros, I'm gonna get 4 zeros here. It's done. Okay. Now, these inputs are 1. That means I don't need to check this input because it's 1. Now I have to move to the next one. These two inputs are zeros. Okay, so they have to be 0. Look what I'm saying? Now let's look at the next one. Here, this one is 1. So this input, these 2 inputs are 1 and 1. So they are not gonna decide what is the output. Okay, I have to look at the first one. The only way to get a 1, here when all the inputs are 1. Okay, if you find one input is 0, you don't need to waste your time. It's 0. Same thing for OR. Just 1 second. Same thing for OR, but in opposite way. Okay, in OR, if I find here, look here, guys, once you find ones, you don't need to look at the other ones. The result is ones. What I'm saying? Here I find ones, so the results are ones. Don't think about it. I find here one input is 1, so it's 1. The only way to get a 0 is when all inputs are zeros. What I'm saying? I hope you understand. I repeated multiple times. This is a Boolean algebra. We don't have addition or subtraction. Instead, we're going to do this operation. You should understand how can you do this operation using 2 variables, or it can be 3 in this case, or maybe more. Okay? We're going to continue this stuff.